And the data set that we are looking at is in like maybe petabytes, terabytes, not like G's. It doesn't work on that. So that is one maybe drawback of this. I just address this one and like we look at this in disadvantages and advantages part. Generally distribution function, and if it is a single like normal, like it's nothing but the probability density function, and the tilde symbol that is here, it's representing the sampling process. Sampling is nothing but the process which I told I'll be tying a person's eyes and we'll be drawing an orange from the box. Right? That process is called sampling. So similarly, when a person drawing an orange from the box, network will also try to sample data from the data set that we have. It will be taking some data, and again sampling here again is IID, because if say for example I collect data set again in our campus itself, it's a video data. It's direct time sequence. I start from the gate, I go till maybe hostel building. So since every frame is dependent on the previous frame, if I just randomly, not randomizing, if I just give the entire data as it is to the network, again like based on the previous input, it can try to get biased on the time series as well. So we have to break that. That's why this random sampling, and there are a lot of sampling techniques as well. It's again an independent research as it's on its own. All the part that we look at, even though they might sound very small, but they are really going to affect the network in a huge scale, especially when it comes to multi-million company like ChatGPT or Microsoft or Google, pick anything. Say for example, when GPT, I think 5.0 came, that is recent. I was checking this in like 2-3 weeks back. GPT 5.0 and GPT OSS. I don't know if you're like even updated, but that is a recent outcome from OpenAI again. So people started commenting saying GPT OSS is not much better, like it's just overfitting, it is just hallucinating. There were a lot of negative comments on the network. So why would a company try to get that on? That just inherently affects the shareholders' things, right? So they don't want to do that. So they will try to focus on each of the smallest part so that those kind of mistakes never happen. And yeah, I think the assumption part I have already cleared. One more thing, sorry. Single unknown distribution. That is one more thing. So here, when I am speaking about generative network, here consider it more like a single distribution at all, alone. Why? Because if you have multiple distribution, what happens is we all know like neural networks are the best function approximators, but when it's given with multiple distribution, it cannot approximate more than one function at the same time. It will just break. So it's better to always keep one distribution alone. So the distribution can be more like a normal distribution, Gaussian distribution. So it can be any of the thing which I mean it's user's interest. And generative modeling. Just a minute. So yeah, getting back on generative modeling. So the key goal of generative modeling or generative AI is nothing but like, as we all saw, it is just to generate or predict an given image or any text. It can be anything. It has to just predict or generate that particular modality. So that is what it says here. The goal is to estimate the probability distribution and learn from it. Learn to sample from it. So when I was saying I am generating an image or text, so it is again trying to sample out from the previous distribution itself, right? So that's what probability distribution that the model is trying to learn. The model, we can assume it again as a function that I will be covering in the next part. So here, just think of it, it is learning some distribution and we have to learn how to sample from it. That is the main goal of generative network. And here, discriminative models only estimate the probability distribution. When I say discriminative models, consider more like a classification example. So I have, say, 5 different diseases of a plant, and I want to just classify in what kind of plant it is, what disease it has. So those kind of networks are called discriminative models here. That's what I'm trying to refer here, where the estimation or the main goal is just to predict, like it belongs to a certain class. It's giving you the probability value. It's not trying to sample anything from the input data. It is just giving you one value. That's all. It can be a regression or it can be a classification. The task can vary, but it's not dependent on the data is what I mean here. While generative model estimate the probability distribution and learn sampling. So it is trying to learn, say, for example, one more use case. I have it on the slide. I just give an intro now itself. So there is a use case for us where we had to generate thermal images for some use case given an RGB image. Why? Because thermal cameras are very expensive, and one more thing is long-range thermal cameras are prohibited in India. It's not legal. You can't import also unless it's government body like defense related projects. Like only military people will be having that access to operate on those kind of camera. But as an academia, we have to work or tackle on that particular problem. So we need data. They won't give the data as easily, like due to their own internal politics. We have a lot of reasons. So we won't go there. The key part over here is I want to generate a thermal image given an RGB image. So this process of drawing a thermal image and how it is dependent on the RGB image is what we are looking at here. It is generating, that means it is learning the probability distribution of RGB image when an IR image is given, like how it can sample it out, and what is the probability distribution of IR images. And yeah, general principle of solving, or this is more like the flowchart kind of assumption you can think. So mainly it can be broken down into 3 different parts. So assume a parametric family of models that is denoted by P theta. So theta here is nothing but the parameters. So in neural networks you all know there are weights and matrices, right? Weights and bias. So these are the parameters that we are referring to here when I say P theta. And define and estimate the divergence metric. Divergence is nothing but like this is to be vague. It is a loss function, nothing much. But since it's mathematical, we like define it divergence metric. So here, when I say divergence, it is trying to estimate the distribution shift between 2 different probability distributions. So that is P theta and Px. So the Px is here and P theta is here. So and solving for optimization problem over P theta. Optimization problem, you can think of it more like the learning process. That is a key part where the network is changing its weights according to the output it has predicted. The weight updation process, which you all know. And yeah, I'll just go on all these 3 steps one by one. And first process is the data distribution P theta, which I was speaking about, right? So consider a random variable that Z that belongs to some arbitrary distribution which is known. For example, here I am considering a Gaussian distribution which has 0 mean and unit variance. So one is a standard deviation over here, and trying to sample from this random variable Z, and when it is passed to a function g of g theta. Again, theta here, so g theta is nothing but the machine learning network, like a model which has theta parameters. When it is given with a random variable z, it will give us another random variable x hat. That will again belongs to some distribution. So you might be thinking, okay, it's just going through a function, so it will just be the same distribution. It won't, like, it can't vary from the input distribution, right? But it's not the case. So that is like again a fundamental principle in probability, where it says that whenever a random variable is passed through any arbitrary function, so the function output will always be some other like Again, it will be independent, like, sorry, not independent, it is dependent on the arbitrary function, but it is not same as the original distribution. So exact is not same as Z is what I'm trying to say here. And yeah, the model G is theta, which takes random variable Z, it maps the input Z to an output X. So then like exact is nothing but the prediction, right? That is coming out of the model G theta whenever an input is drawn from the random variable Z. So given samples from known distribution, the network transform it to other distribution. That's what I mentioned previously now also. So the exact is again not same as Z, but it is dependent on Z. That is one thing which we all have to remember. Like it's a very hard thing of probability. And solving for optimization. Now we got some output. So the output is belonging to some distribution exact. Now we want to optimize the network. Like exact initially can be anything, like right? It can be some noise, it can be some garbage value, anything. So, but we want to optimize such that it is fitting to our task. That's what we are looking at when I say solving the optimization problem. So here again, theta is the parameters. Theta star is nothing but like the main objective of optimization is to minimize the weights of the network. That is parameters theta. Whenever like for a given divergence metric, the divergence metric here is defined over T over like two probability distributions, P of X and P of theta. So like P of X is the original distribution that is belonging to Z here, and P of theta is nothing but the probability distributions that is coming from the output probability X hat. So we try to minimize this. When I am trying to say minimize, like what we are trying to like achieve over here is the process of network learning for a given input there is the output. That's what we are trying to say here. It has to be minimum, like it has to be more looking to the original part, it shouldn't be diverging. So when I say diverging, more like if I ask for a lab, it shouldn't give me laptop charger and be like, yeah, this is the lab, right? So yeah, it has to give specifically laptop alone. That is what we are aiming at. So this particular equation will try to solve this, and we'll look at different divergence metrics also. And yeah, divergence of this metric, minimizing the divergence representation between two probability distributions. That is what this equation is doing. And one more key important factor here to consider is whenever we are using any divergence metric. So it's again like dependent, like say loss function. It's on us, right? Like whenever we are constructing the neural, we can choose whatever loss function we want. But there are some ground rules what we have to follow again for all this process. So the divergence metric should be chosen in such that it's not negative. Right? It's not negative all the scenarios. Like intuitively, if you think, can a loss function be negative? No, right? Like loss, if it is negative, like it doesn't make any sense. It should be like positive. Like it's varying by some certain value. Say for example, even in academia, do we give negative marks for any people like students? We give 0 if they we don't give negative as such. Negative doesn't make sense. That's what here also I'm trying to say. And therefore, like sampling Z passed through G would give a probable sample from P theta that is close to X. So this is the main goal that again is denoted in the first equation. So the divergence metric again is defined over like with the term F divergence particularly. So yeah, divergence metric over two probability distributions Px and P theta is defined as the integral over like X that is sample from probability distribution P theta whenever an input random variable X is given times F is an arbitrary function over here times like the ratio of two probability distributions. So this is the fundamental formula for all the divergence metrics. They are defined based on this. This is more like the template for divergence metric is what we can assume. So yeah, F is an arbitrary function that maps from real value numbers from positive values to another real value, it can be positive. So again, like F cannot be negative. Why? Can I even say like F can't be negative over here? factor. And properties of F divergence include non-negative for any choice of F, that is the arbitrary function, and zero only if and only if if two distributions are equal, and if p theta equal to px in this condition. So here are some divergence metric examples, the popularly known ones. So first one is the K divergence. Like you ask any ML guy, he should be aware, he will be aware of K divergence metric that estimates the probability distribution over two distributions. So here p of x and p theta. So here this one p theta of x is alright. This one. So here it is considered as px of x. That's all. This is a very name. This is the oldest and it's also a classical technique which we all still use even till date. Even in our lab, we still have some networks which are defined over K divergence loss. So yeah, that is one. And Shannon divergence, it's again a derivative from the K divergence itself, and total variation distance. So the derivation part I won't be touching upon right now here because of time constraint and other factors. So yeah, we'll just get on to GAN. Are we supposed to take a break or? So I'll start with GAN paper. So I don't know how we have taken when you all enroll for this course. By any chance you will check what is GAN, what is the original paper, who is the author, why is this important, all these things. By any chance, that curiosity was it there? Sir? I am good fellow. Yeah, good fellow. Yeah, he's more he's a disciple of a great professor called Yoshua Benji. So this professor is again from Mila, Canada, Quebec. So yeah, the godfathers of AI domain, which rule till now, that is mainly three people. The list goes on, but I know mainly three people which I admire at least. That is Yoshua Benji and Geoffrey Hinton, as you all know, he got Nobel Prize recently for AI. And Jan LeCun, of course, he's the director of Meta Research. That's very. Again, Jan LeCun, he is again from NYU Quran, and Geoffrey Hinton, he retired. He's not teaching anymore. He stepped out from even Google. So yeah. This paper is again from Ian Goodfellow. There is a textbook written by this particular professor, Ian Goodfellow. You can check it out. It's called Deep Neural Network or Deep Learning. Deep Learning by Ian Goodfellow. You can search it out. It is really good textbook, which is more considered in all the international schools as a basic thing to go through. That's used as a reference textbook. So, yeah. This was the original work that came in 2014. So the work on generative AI was not this was not the first work to start, but there were some classical approaches prior also. For example, the Markov chain and other graph-based networks were used. But this is the first network, first work to use deep learning, where you bring in a function approximator, which is totally all these neural networks are called black box, right? We don't know what's happening behind. So it's just even till date, ChatGPT's creators doesn't know why it is predicting. They are still figuring out why it's happening. Let's say if you are interested, go through this speech by Geoffrey Hinton. Even in that, he says AI is actually scary. Is what he says. Why? Because no one knows, no one can explain why it is performing like that. So even the top people are actually scared. There are drawbacks as well as good part. So when such kind of sophisticated technology goes in wrong hands, again it will lead to chaos on it. So that's what. Black box. So that's what we call. If something is totally unknown, why it is behaving like that, that's something we call black box. We also have white box networks. For example, I think physics and neural networks. I think it's trying to map these two together. So what happens is the generative network, whenever it is passed, the G theta, if you remember from the previous slide, it is nothing but the generative network. Whenever a given random input that belongs to probability distribution, Z I denoted previously, it gives a sample output, right? That is belonging to again a P theta which I told you. So this is nothing but the process of distribution. It is learning the probability distribution, and from these two, it has to learn sampling. Like again, the key goal of generative AI, I told it is nothing but learning the distribution, learning the sample. So here it is learning the distribution, and here it is trying to learn sampling process. So again, real images are there. It has predicted some image, like when a given image is there, correspondingly it predicts something. This is again passed to a discriminator network. So again, like discriminative models I told you, right? It's just giving you some value. It's not like generating anything. For example, classification as I said. Here also it's the same thing. It is just discriminating. It will say if like this there is a funny example as well for this part. I'll just go over in the next slides. So yeah, it has to discriminate between the generator's samples. So it will give two losses. That is the K divergence if we consider between these two probability distributions, right? We get loss, and that loss drives the generative network. So it updates the weights of generative network over here and discriminator as well. So these two are combined as the loss function. I think that is also provided here. And here I am speaking on only one modality, that is random input and a sample, right? You can even condition it based on some other modality. For example, text we can consider. In this slide, we see both generator and discriminator has two specific inputs, X and Y. So X can be a random input, Y is a conditional input that we are trying to feed into the network, and it is giving us a probability distribution. So this one is nothing but a conditional probability distribution. Right? There are very two types, like conditional and marginal probability distribution. Right? So here we are looking only on the conditional probability distribution for a given model. When it is like considered considering X as an input, and it is considered condition of X. So the example that I wanted to make here, say for example, how many of you have watched this series? Percy? Anyone? Yes. So the hero or the main guy will be trying to print fake currencies, right? He will try to scam, and of course, Vijay Sethupathi will be there. He will be chasing this guy to identify the process of identifying. So I just correlate some of the characters in that series. So say Vijay Sethupathi, a guy, the police cop, is nothing but a discriminator here, and the main hero is nothing but like the generator here. He is generating the fake currency. His goal is to make sure the police doesn't catch him. He has to just make money. That's all, without any government thing. So he's trying to fool the discriminator or the police cop. In fact, in the other hand, if you think of it in the police perspective, his main goal is to identify fake currency. He has to know which is real, which is fake. He doesn't care like how it is generated or something. So yeah, he shouldn't get fooled, and generator should try to fool. That's what is happening here also. The generator network over here will be trying to predict some value or some image, which will be the motivation for generator is to fool the discriminator. Whereas for discriminator, it shouldn't get fooled. It shouldn't follow the path. It should always identify if it is a real or fake currency. So when I say real or fake currency, the discriminative process, again, like getting back to the mathematical thing, coming back to movies. So it is trying to discriminate or classify if a given sample is coming from this probability distribution or this probability distribution. So this generative probability distribution is of P of X, P theta, right? So if over here. That is the main goal. So yeah, this is a classic example, and yeah, the generator learns to generate the data, and discriminator learns to predict generator's data if it is real or fake. And the discriminator penalizes the generator for producing implausible results. So here, this is a process, like figure illustrating the brain process of a generating network. Let's say it is estimating the probability distribution. So initial figure like A, B, C, D is there, right? So initially it starts with A, where the blue dots indicates the discriminator's probability distribution. Initially, if you see, there is a great variance between these two distributions. Divergence metric, even if you consider distance metric, Euclidean norm or some L1 norm, the distance between these two is very high. It has to be minimized. So that is what is happening here. Initially, the distribution is very high, and then whenever when we bring in a generator, these two processes involves like bringing a generator, and after we bring in when we train, this is how the final output will look like. It will try to fit into this dotted line. The green one is the generator's probability distribution. So yeah, that is what this figure is trying to illustrate. And this is again taken from a paper from Neurons itself. We also on Neurons conference, right? So back in 2014 itself, this paper has got published, and again it is from Neurons itself. And this is an algorithm explaining like the generative part. So for a mini batch of stochastic gradient descent training adversarial networks, so we have a set of data and we specify the number of iterations till when the network has to learn over, and that's what we sample it out here. For case steps, we take again like in generator, I one more thing. It is not taking only image as an input; it is adding noise to it. So yeah, I told you right. It has to. Main objective of generator is to like yeah. Can anyone say? Recollect. What is the main goal of generator? With respect to discriminate. Yeah, correct. So it has to fool the discriminant. It has to generate the fake samples, right? How does it do? It will add noise to the modality. So when I say noise, it can be any perturbations. Perturbations are the distributions that distribution shift that I want to explicitly add in for a given modality. For image, I can consider if I erase few pixels. So image is nothing but a h cross w pixel, right? So if I remove some pixel values, it might be still interpretable. It might be in a manner where at least humans can interpret, but a network won't interpret. So this is an adversarial process. Like there is again a research domain altogether on this particular part, which they call like adversarial attacks and adversarial learnings. So the network has to be learned. There is one more paper, I think it got published last year. It was quite interesting. For a transformer, if I add only one dot, only one pixel on a given image, the network will crash. It is known for even GPD and Llama, all these networks. They are actually proven here. When they add one white pixel on a given image, if the image had panda, original input, it will start identifying it as an horse. Like that kind of impact is what we are looking at here when I say adversarial attacks. So I'll try to arrange it when I get a tea break. It is quite interesting. You can still look on it. So like how easily you can break a charger or something like this kind of works are also quite interesting. So yeah, it is trying to sample the noises also, that is denoted as M, from the distribution, probability distribution capital Z, which has samples Z1 to Zn. And the mini batch of M, which will have the examples, that is this is the original data set. X refers to the original data set and Z refers to the noise for generating. So the final probability distribution the network will be giving out will be the data of X. So update the discriminator by assigning its stochastic gradient, and when I say this is the optimization part. So there loss function with respect to the weights, and then whatever value I get, if it is positive, I will change the weights in positive manner. If it is negative, so turn it in the negative manner. Yeah, I will be seeing that. So it's not like manually I will be seeing, but the network will be in turn doing that. That's the process of optimization. It will try to minimize this loss function or the divergence metric. That is the main goal. And yeah, finally, you will try to sample the mini batch M noise inputs from Z, and yeah, update the gradient descent in stochastic, gradient descent algorithm, that is stochastic gradient by here. Yeah. These are some of the outputs by the initial work that was published in 2014. Again, if you all know, I don't know, like MNIST is like a classical data set. It's not quite huge images. It's just 32 crossover pixels max. I think its original dimension is 64 crosses. 60 crosses. So yeah, now that we are all looking at iPhones which can generate 4K resolution images, back then we were operating on 60 crosses, and the process was just to generate a given number from another input distribution. So in the first image A, you see like the left column, right, that I'm pointing to. This is the original input, and the final input is this high level part, where this looks more like a 7, but it's clearly recognizing it as 9. And this is the learning process. So like each column here refers to, like, consider it more like an iteration or a log. Maybe in the first iteration it identified as 3, second iteration it identified more like a 9. Again it is fluctuating, and then finally it's okay, settling down. This process, like, again, it is, I just go into the main thing. So this process is called convergence. So that's what we all look at. The model has converged to the given output. Like, it shouldn't diverge is what we all say in technical term. So after convergence, you see like the input predictions, like the output predictions are quite massive in the input one. So yeah, first one is digit recognition, and second one is for facial image generation. So, and C and D are the input noises which are getting added even after adding the noise or even on top of low resolution. So there is one more criteria. Again, like this application I will try to recollect in the future slides. Please remember, for low resolution images, I am trying to extract what the given object is. Yeah, that's what it is. It is quite neatly identifying. Usually it is blurry. It is identifying the aircraft, maybe a cat, or an all properly. Do you need a break or is it just tiny? So again, like this part, we will be looking at the advantages and disadvantages of CAM, as I was telling you yesterday. I mentioned maybe one or two points in the initial part about the advantages and disadvantages. This is like proper classical, like formal stuff. Advantages of generative, again, like high quality data generation. For example, here in this previous output, you saw the input images were corrupted, but the output image, compared to the input image, is quite like clear, and it is of better resolution. So that's what we say here, like high resolution, realistic data generation. That is one advantage. Versatility across domains. So this is the same concept which I told previously: image, text, and speech. If it can interoperate on all three domains, it is much better. Right? So that is one advantage which we get here. The conditional GAN, which I showed you previously. So yeah, this is one more advantage where we are able to condition on some other modality. Say I have an image, for example, DALI takes that. In DALI, I pass an image. I also have a textual prompt box. I will say remove zebra from the image and replace it with a flamingo. I think that is the typical example which I provided back then. So whenever this process is again called like in painting technically. So replacing an object can be conditioned through texturing. That flexibility can just provide. So that is one more advantage. And unsupervised learning. So unsupervised learning capability mainly because in the previous term also I that process we need unsupervised learning and data diversity for a various kind of data set. It can still interoperate. So these generative AI or DALI networks are trained from mainly like Instagram images, Facebook images. It can vary differently. Like the diversity is quite huge. It's not specific only for one use case. It's from different backgrounds altogether. That is one more advantage that generative AI offers. And reduce human labor. Human labor is reduced mainly because the process of data generation is a quite hard process. Like, for example, technically, I think when you visit our lab in IISc, you know like there is a Unreal Engine and 3D simulators, Scala and all. So that takes a lot of time and resource, and you need manpower to generate those kind of data sets. Whereas if you have a generative network, if you just pass an image, it will give you the corresponding output, right? Like it is much simpler and it is not even for the person who is operating, since it is a redundant task of generating data, he will quite become bored at some point. The breaking threshold is like for humans is very near. If I were to sit and annotate a data set, I will break down maybe in 2-3 days. Like I can't sit and keep annotating, right? My brain will just become dead. I don't like that. So we in fact bring pre-trained networks to annotate or even generate the data set for these kind of aspects. And there are quite disadvantages also in this part. So training instability. So initially I was telling like if the data distribution again has some bias, the network will try to learn the bias and it will overfit, right? So and also one more thing, this adversarial attack where I said adding one pixel, it will just crash in. These are nothing but they fall under the training instability. That means the network hasn't learned to generalize much better. The data set, it hasn't learned upon it properly. And yeah, model collapse is on the same part. Sensitive to hyperparameters. For example, if I choose my divergence between something different, it will have again quite a few like different impact. One more, instead of divergence metric, consider iterations or epochs. If I keep very short epoch, again like you should give some time for the network to learn, right? If you are limiting on that, the network won't learn. Something similar to even students. If we provide time, they will learn. If we just ask them to maybe cover one module in one day, they won't learn. They wouldn't be able to grasp all the key concepts in that particular module. Same thing here also. And complexity of the network is again a main disadvantage, right? Because I mentioned previously, right? Like these are like games for big games, and that is ChatGPT, OpenAI, Microsoft, Gemini. Why only these people are publishing papers? I mean, like Yoshua and Joe, these people are related to I think Ian Google was in Google back then. So yeah, they have the resource to handle these kind of models. Whereas if you ask maybe like some random institutions, they might not have that kind of resource to handle the data set or the models. So these models are quite big. One more example I will just give on personal experience. We tried training a camp, and we have RTX 6000 cards GPU in our lab. There are I think 4 of them. We had 2 of them working especially for the camp training network, and like a number of images were like within like 10,000. But to train camp on those kind of small data set, it took 4 days for us. And each GPU had 49 GB card. Just imagine, this laptop has maybe like what 16 or max to max it can have 32 GB of graphic card, not more. But this alone cost me around like 3 lakh, 4 lakh, right? When I'm thinking of 4090s and all, it cost me 15 lakh. So that is for a single card, not for even the server. But if the network is not able to fit on smaller devices, that kind of compute is needed. The complexity makes it harder for even the common people to access. That is one thing. One more key interesting factor I will just draw on. ChatGPT requires like I think 24,000 liters or something fresh water to cool down their servers. And their servers are like there is one more part. I think Google is trying to retrieve dam, which was shut down in Pennsylvania. The 3 Mile Island, I don't know if you have seen, it's a disaster area, and they are trying to retrieve it back. Because these models need that kind of power for all this complexity. So without that, it's not possible. Or in that case, Google won't be releasing this Gen AI and all, right? So yeah, that's what is powering. The complexity makes it harder for the common man to access this order types. And lack of excess density estimation. So the KL levels and other metrics which I showed. So these are like the classical approach. We are still not trying to figure out moving on new metrics. So this is dependent on numerous factors like the data set or the network again. So this again brings a limitation on Gen AI. So yeah. Here I will be covering some application. This is one more paper. It got published in Syria. Again in 2019. This was a motivation for research that I was doing. I'll be talking on that one as well. It's again somewhat related, but this work is again fully related on what we are looking at right now. So on the left, you see a couple of images, right? The clustered image, which is quite, I don't know, it just has some blocks rather than cars. So this is the output of generating a thermal image for a given RGB image. When I have RGB image, I want to generate a thermal image. You see, the network is failing, it's not able to grasp that kind of knowledge or distributions from input, that is RGB domain, to thermal domain. So here they have considered cycle cam and unit. These two are recent networks. I mean, recent when the paper got published, but now it is quite outdated. So considering over there, they have generated the output, and this process is called domain adaptation, where they have so domain adaptation is something more like I have two networks. I want to adapt. So previously, you remember I was telling I want to sample or generate an image of a laptop from a car, but the training data is taken from a classroom, right? The data distribution is quite huge. So to tackle that, we follow this concept. Like there is a paradigm called domain adaptation. So the key part over there is to minimize the domain shift that happens between two distributions. That's what we are trying to do even here. There are two domains, that is RGB and IR. They are quite totally different. The only similarity between RGB and thermal camera is the structural aspect. The semantic aspect is totally different because thermal camera won't have any color information, right? So given a car, be it where you have anything, it can say it is a black or a white car. It doesn't capture that information. It's not the use case of thermal cameras either. But whereas in RGB camera, I can still capture the color information, and based on the color information, I can still get fine-grained features, right? So, but I want to adapt from this domain to this domain. End of the day, I want to predict from thermal data set as well. Is very good, without forgetting the previous domain, that is RGB. So this is talking about the feature alignment aspect, where I have two separate encoders. I pass the image, I get features. And here they are essentially concatenating these two features and passing it to an RPN. RPN is the region proposal network. Here the main task is object detection. That's where RPN is coming into the picture. Or else if it is a classification, I will use a software classifier and call it for the day. But for object detection, we need RPN networks that can predict the regions where an object can occur and what the object is. That's what it is trying to do here. And yeah. These are some results on the paper. So this is the input data. On the top as you see, right? These are the input images where they have thermal data set taken from FLIR and one more data set called KAIS. KAIS is a Korean research institute. Like this data set is from KAIS, and FLIR is from this commercial body. FLIR does provide all these thermal cameras. If I think any institutions are looking on these kind of networks or these domains, I think FLIR provides RGB and IR cameras that are really good. Apart from that, there are again other providers. Indian providers are not that they are still trying to reach it, but they have started like backing. Those days itself, you see the resolution of thermal cameras, it's quite better. Yeah, they were dominating from a long time. Whereas India is just picking the pace now, but yeah, they will reach there. So these are some of the qualitative results of the object detection on both flood and gas data set. So first row indicates the flood and second is the gas. The opposite way. Yeah, this is flood, this is gas. Okay. So on the networks. So and the accuracy metrics, the qualitative and the quantitative part is denoted here in the table below. So you see the baselines, right? These are nothing but yeah, baselines are nothing but the prediction results from thermal data alone. It is not like looking at the RCB image at all. But yeah, these are the original source which we call again oracle is what we term it. In any paper, if you see oracle or source accuracy, oracle is directly evaluating on the target. Source is on the it is trained on data set A and it is tried to test on data set B and or something. So here it is oracle and the performance are this one. After they use the GAN, so unit and CG cycle GAN, they are illustrated in two different tables. So here, if you see, it outperforms the existing baselines. So, and yeah, baseline, sorry, one more small confusion here. Baseline doesn't really relate to oracle or the source unit. Baseline is the previous network's output. Like till the time, whatever the state of art network is performing, that we consider it as a baseline. We need a reference. Say for example, KAIS published I think in 2012 or something. This is 2014, I believe. So yeah, there are a lot of works and till 2019, whichever network had achieved whatever the maximum performance, that is what I am assuming as baseline here. And compared to the baseline that is previous works, what is the accuracy that I am getting here? So it beats baseline in both when it is using unit and cycling GAN. In person class usually it's 54 and is going up to 59, 67 going up to 70, 53, 59. So yeah. And Evers, Coco and Pascal POC are again a large scale data set which are used for a variety of tasks like classification, parametric segmentation. There are a lot of tasks again on both these MS Coco and Pascal POC. They are considering RGB images from these two and they are evaluating on the target that is thermal images. They are not considering co-registered images.